The concepts of oxidation and reduction can be a little confusing, so let's have a look at some of the basics here. First, let's consider oxidation. It's been defined a number of ways over the years, and one of the earliest definitions is simply when an element reacts with oxygen, which obviously is where the term oxidation originated. For example, magnesium reacts with oxygen to form magnesium oxide, under the right conditions, of course. Need to balance that equation. So you would say that the magnesium has been oxidized to magnesium ions. Magnesium oxide is an ionic compound made up of a positive and a negative ion. So the magnesium in its elemental form has been oxidized to magnesium plus 2 ions. Or you could say it's accepted or reacted with oxygen, which is in agreement with its early definition. But it turns out you don't necessarily need oxygen to have oxidation. There are many oxidation reactions that occur without oxygen being involved. Let's see an example. All metals, at least most metals, react with most acids. Of course, there are exceptions, but in the case of magnesium, it readily reacts with hydrochloric acid to form magnesium chloride plus hydrogen. And that, of course, needs to be balanced. Again, you would say the magnesium has been oxidized to magnesium plus 2 ions. No oxygen was involved. So both the reaction of magnesium with oxygen and magnesium with hydrochloric acid are oxidation reactions. So we need to ask the question, what do both of these reactions have in common that make them oxidation reactions? I think it's pretty obvious, but let's see what happens to the magnesium in each case. First, with oxygen. We'll stick with magnesium, reacts with oxygen, and it forms magnesium ions, plus 2. Magnesium with hydrochloric acid forms magnesium ions, plus 2. So in both cases, the magnesium has gone from the elemental form with no charge, neutral element, to positive ions. The magnesium has gone up in its charge to form a cation. So another way to define oxidation that is much more comprehensive is to say when there's an increase in this charge, oxidation occurs. Now that charge we often call the oxidation number or the oxidation state. So a better way to define oxidation is the increase in oxidation number of an element. When that happens, it's been oxidized or oxidation has occurred. This definition, of course, works for any element, not just magnesium. So if you've got something like copper going to copper plus 1, that's oxidation. If you've got gold going to gold plus 3, the gold has been oxidized. It also works for nonmetals. If you've got nitrogen, -3, going to nitrogen 0, it's gone up in its oxidation state, in its oxidation number, it's been oxidized. Now we need to ask the question, what's actually occurring when an element goes up in its oxidation number? What's taking place with the element when it goes up in oxidation number? So back to magnesium again. So no matter what it reacts with, whether it's oxygen or an acid, when it goes up in charge, what's happening? Is it picking up 2 protons, for example, to become more positive? The answer is no. So let's see what's taking place when oxidation numbers increase. This actually leads to another definition of oxidation, perhaps the best definition, and that is it's the loss of electrons. And that's a little hard to see sometimes. When a neutral atom of an element goes to a positive ion, magnesium goes to magnesium 2+, what actually happens is the magnesium loses 2 electrons. And because electrons are negative, losing something that's negative makes the product positive. Now, we don't normally write that equation the way you see there. We put the electrons on the other side. And so we write it like this. Magnesium goes to magnesium ions plus the 2 electrons. So what we're saying is that the magnesium has lost 2 electrons to form magnesium plus 2 ions, therefore it's been oxidized. So 3 ways to define oxidation: the addition of oxygen, number 1, an increase in oxidation number or oxidation state, number 2, the loss of electrons, number 3. Let's examine that loss of electrons a little bit more closely. So magnesium is element number 12 in the periodic table. It's got 12 protons and it's got 12 electrons. If magnesium loses 2 electrons, it then has 10 electrons remaining. Still got 12 protons, but only 10 electrons. So overall, it's got a charge of +2. Magnesium, the element, loses 2 electrons to become a +2 ion. And if you're wondering, why does magnesium, for example, lose 2 electrons? It all has to do with the electron configuration, which for magnesium is 1s2, 2s2, 2p6, 3s2. That's a total of 12 electrons. Magnesium has got 2 electrons in its outer shell. Electrons are lost first from the outer shell. Atoms like to have filled outer shells, so by losing those 2 electrons, and not 1, not 3, by losing 2 electrons, it now has a filled second shell, which is stable. So magnesium always forms magnesium +2 ions. Sodium always forms sodium +1 ions, because sodium has got 1 electron in its outer shell. Aluminum likes to form aluminum +3 ions, because it has 3 electrons in its outer shell. It's not quite that simple for the transition metals, but for the group 1, 2, and 13 metals, it's fairly easy to figure out what the charges on the ions will be just by looking at the outer electron configuration. Now let's turn to reduction, which we considered the opposite of oxidation. So we can define it as the loss of oxygen or a decrease in oxidation number or oxidation state, or the gaining of electrons. In other words, gaining electrons will make an element or ion go to a lower oxidation state or oxidation number. Let's use the magnesium oxide example again. The reverse reaction of the very first one shown here would be this. The magnesium oxide going back to magnesium plus oxygen. You need to balance that. So here, the magnesium starts out as a +2 ion, ends up as 0. The magnesium has been reduced. The magnesium ion has been reduced to magnesium metal. It's gone down in oxidation number. It's lost oxygen. And if you look at it a bit more closely, you can see that what's happened to the charge is it's gone down from +2 to 0. How can it do that? By picking up 2 electrons. So writing that reaction out again, magnesium ions pick up 2 electrons to give magnesium in its elemental form. That's a reduction reaction. The magnesium ions have been reduced. Now, it should also be mentioned that whenever you have oxidation, you'll always have reduction. So for this reaction that we started out with, magnesium plus oxygen to give magnesium oxide, there is both an oxidation step, the magnesium gets oxidized, and the oxygen gets reduced. You can't have one without the other. Now you can consider them as separate half reactions to discuss them, but in practice, one needs electrons, the other produces electrons, so they complement each other. Let's break the magnesium-oxygen reaction down again. So magnesium plus oxygen gives magnesium oxide. That's the overall reaction. It's made up of 2 half reactions, an oxidation step and a reduction step. The oxidation is the magnesium going to form the magnesium ions, and it produces 2 electrons. That's the oxidation step. Magnesium gets oxidized. It loses 2 electrons. But what about the oxygen? What's happening there? So the oxygen goes to form the oxide ion. Now, how does that happen? Well, that's a reduction step. If you look closely, the oxidation number has gone down. Oxygen is 0, goes down to -2, so that's a reduction. How does that happen? Well, along comes these 2 electrons and reacts with the oxygen, reducing the oxygen. Now that, of course, needs to be balanced. You notice the oxygens are not balanced, so if we put a 2 here to balance the oxygens, the charges are no longer balanced. There's a total of -4 now on the right-hand side, so we have to change this to a 4. Now it's all balanced. Then what we can do is add the 2 equations together. If we add that equation to that equation, we will get the above equation. But we still have to do one more thing. We have to multiply the first equation by 2 so that we have an equal number of electrons. 4, 2 of those, 2 of those. So then if you add the oxidation step to the reduction step, you'll get this overall reaction. A common term that we use to refer to oxidation-reduction reactions is redox reactions. And another couple of important terms that you need to be familiar with is seen here. Going back to the magnesium oxide example. Again, we say that the magnesium has been oxidized, the oxygen has been reduced in this redox reaction. One produces electrons, one uses up those electrons. Two other terms that you really need to be familiar with are the term oxidizing agent and reducing agent, or oxidant and reductant. If the magnesium is oxidized, we have to ask the question, what is causing the oxidation? And that, of course, is the oxygen. The oxygen is the oxidant or oxidizing agent. It's causing the magnesium to be oxidized. So it's easy to get those two confused. The magnesium is oxidized, but it's the oxygen that's doing the oxidizing, so it's the oxidant. Conversely, we can ask the question, what's causing the oxygen to be reduced? Well, of course, that's the magnesium, so it's called the reductant or the reducing agent. The magnesium is reducing the oxygen to the oxide ion. In fact, metals are very common reducing agents used in synthetic chemistry and preparative chemistry. So it can be a little bit confusing with all these terms. Make sure you can understand each one and appreciate their significance in redox chemistry. Finally, what about assigning oxidation numbers to elements in compounds? How do we do that? That's important so that you can determine if a particular half reaction is an oxidation or a reduction. So again, using the magnesium oxygen reaction, all elements have got no charge, therefore they've got zero oxidation number. So oxygen, magnesium, both have zero oxidation numbers. But ionic compounds, it's very easy to figure out the oxidation number of the elements in those compounds. They are simply the charge on the ions. So magnesium +2, oxygen, oxide, -2. We can see that magnesium has been oxidized, oxygen has been reduced. So again, ionic compounds, very easy to know what the oxidation states are. Not quite so easy for covalent compounds. There are rules that we have for assigning oxidation numbers to help figure that one out. Covalent compounds, that's a bit trickier to figure out the oxidation state. So let's consider this. Hydrogen plus oxygen forms water, under the right conditions, of course. Is this an oxidation-reduction reaction? The answer is yes. How do you know that? By looking at the oxidation numbers of all the elements in the compounds. And you'll find one element goes up in oxidation number, one goes down. That is, one element is losing electrons, one element is gaining electrons. It's not quite so obvious in compounds that are covalent as opposed to compounds that are ionic, because there are no ions in water. So to figure out what's going on here, we have to go back to some rules for assigning oxidation numbers. Now your textbook has got those rules, so it's important to make sure you know those rules when studying oxidation reduction. Some of those rules are elements have zero oxidation number. Whenever an element is present in a chemical reaction, magnesium, oxygen, hydrogen, those elements have got no charge, no oxidation number, all zero. So look for an element in a chemical reaction, and it's by itself zero. When it's in a compound, the oxidation number is almost certainly going to be non-zero. So rule number 2, if you're dealing with an ionic compound, the oxidation number will be the charge on the ions. That's why magnesium was +2, not only its charge, but its oxidation state. Oxide was -2, its charge and its oxidation state. Now, what about the hydrogen and oxygen reaction? What's going on there? Well, again, hydrogen and oxygen on the left-hand side are both elements, so zero oxidation state. One of them is getting oxidized, one of them is getting reduced. One of them is accepting electrons, one of them is losing electrons. How do we figure out which is which? We need another rule, especially for hydrogen. When hydrogen is combined with a metal in a compound, its oxidation state will always be -1. When hydrogen is combined with a non-metal, its oxidation state will always be +1. So we ask ourselves what's going on with hydrogen in this reaction. Well, it's combined with oxygen, a non-metal, so the oxidation state of the hydrogen must be +1. What about the oxygen? Well, there's 2 hydrogens, each having a +1 oxidation state. That's a total of +2. Since there's 1 oxygen in the chemical formula, it has to have the equal and opposite oxidation state to balance it out, because overall it's neutral, so the oxygen must be -2. And oxygen almost always is -2. There are some exceptions, and the rules in your textbook will indicate the exceptions, such as in the peroxide ion or the superoxide ion, but for most compounds you'll find oxygen is -2. So what's going on here? Hydrogen has gone from 0 to +1. It's been oxidized. Oxygen has gone from 0 to -2. It's been reduced. So the 2 half reactions can be written out separately, adding electrons to give you, when you add them up, the overall balanced equation. So that oxygen rule can be number 4. Oxygen is almost always -2. Again, peroxide, superoxide, it can be different to that. And there's another rule, number 5, which is for fluorine. Whenever you find fluorine in a compound, whether it's ionic or covalent, it's always -1. What about all the other elements? Well, usually you can predict the oxidation states of the other elements by knowing these first 5 rules. Let's calculate the oxidation states for all the elements in sulfuric acid. So first one, hydrogen, is combined with non-metals, so hydrogen must have an oxidation state of +1. Oxygen, we're just going to assume here, as I said before, it's almost always -2, which leaves sulfur. Sulfur wasn't in one of the earlier rules, so again, usually there will be one element which you have to calculate the oxidation state for based on the other 5 rules. And so what you do is set up a simple algebra problem. Hydrogen is +1, oxygen is -2. What is sulfur? The sum of the oxidation states always has to equal 0 in a neutral compound. So there are 2 hydrogens, 1 sulfur, and 4 oxygens. So 2 hydrogens, you multiply that by 2. 4 oxygens, multiply that by 4. What does that give you if you add them up? That's +2 minus 8 gives you -6. So the sum of the oxidation states of the hydrogen and the oxygen are -6, which means the sulfur has to be +6 to balance it out. -6 plus +6 has to equal 0. So the sulfur has got an oxidation state of +6. It's that easy.